Today I'm going to talk about some work that I do as part of the ARIAM Hub in collaboration with our partner Thales. And so this is all to do with a project at Garden Island here in Sydney, which is what you can see pictured here. I'll explain what that is. And so, yeah, I'm going to be talking about towards a digital dock, automated planning for keel block reconfiguration at the Captain Grade Wing dock. So this dock that you can see here, so for any of you that I know most of you are down in Melbourne or Victoria somewhere, yeah, but for any of you that know Sydney, yeah, if you come to Sydney and you stand where the Opera House is and kind of look to your right, you'll be able to see often the ships kind of tied up probably just outside the dock here. And so this is the dry dock that is used for maintaining ships. So what you can just see here, actually, just to kind of explain this picture to start with, yeah, just in the bottom left corner here, you can see the water. This is the harbour, and then you can see they've put this gate in. They call it the caisson, which is the barrier that prevents the water getting into the dock. So they've taken these ships in and then pumped the water out so that they can do maintenance on the underside and so on. So really, this whole project is about the period in between when they have ships in the dock and they need to kind of set up for the next ships coming in. And so I'll explain a lot more about that. But kind of before I kind of jump into the talk today, I guess I thought I'd just quickly sort of explain what ARIAM is, who we are. So ARIAM is Australian Robotic Inspection and Asset Management. So we're a research hub at the University of Sydney. We're part of the Australian Centre for Robotics. And really all of our work is to do with using robotics and the kind of tools of robotics to aid with the asset management of major assets, whatever they are. And so I think this diagram in the top right of the screen here is the sort of best explanation of what we do. So we use a kind of combination of sensing and perception techniques, mapping and insights methods to assess assets. And then we use other techniques in terms of planning and control to kind of manage those assets in some way. And so there's robotics kind of involved in all parts of the both sensing and perception and the kind of actual maintaining of assets and so on. And the kind of bridge between those different bits is the kind of digitization of those assets. And yeah, just kind of a really quick overview of some of the kind of companies that we work with. So this is a non-extensive list, but yeah, they sort of broadly all kind of fall into these different categories. And so we have companies that we work with in relation to, you know, they are companies that provide these tools to kind of do assessment and inspection of assets. And then we also work with other companies who are asset managers. So, you know, in this example I'm going to talk about today, Thales, they are the manager of the dry dock asset at Garden Island. We also work with companies like Ansto and BHP who, you know, have significant assets to maintain. And then we work with other companies that are kind of, you know, small startups or small sort of SME type organizations that maybe make different things. So for example, this kind of legged robot you can see here on the right is made by this company Nexus, and it's used to kind of crawl into spaces and do inspection in places that are kind of hard to reach. Yeah, or some of the other companies like TrendSpec, who they kind of make these, you know, 3D reconstructions of various things using aerial and satellite imagery. Yeah, Emerson, who they kind of make scanning technology and mount them on drones and things, or Reach Robotics, who make kind of arms that are specifically, they have an interest in kind of underwater robotics and building these kind of arms to mount on underwater robots for various activities. So that's a little kind of overview of ARIAM. So today I'm going to talk a bit more about the work that I'm doing with Thales in relation to the dry dock. And so, you know, I'll just explain a little bit about what Garden Island is and what the dry dock actually is and what is the challenge that we are trying to address. And then I'll kind of jump into a little bit about how we kind of formulate this problem. I'll talk about the kind of big vision for Garden Island and a kind of fully automated dock. And then I'll talk a little bit about the kind of methodology, the actual kind of optimization approaches we apply, and how we kind of work with Thales to develop them. And then I will talk about the kind of future roadmap that we kind of see for this work going forwards. So yeah, before I really kick off, I guess just to acknowledge that this is a very collaborative project. So my colleagues, Professor Ian Manchester from University of Sydney, and then also colleagues, Professor Hannah Kuati and Patrick Haslam from ANU, who are all part of the ARIAM Hub. I forgot to mention the ARIAM Hub is a collaboration between Sydney, ANU, and UQ. So on the academic side, but then also key to this project is our colleagues from Thales. So Andrew Seal and Inez Smith, who are the kind of key advocates for this project within Thales. But then really important for this project is Brad Lovegrove, James Johnson, Chris Campbell, who are the dock operations team. So Brad Lovegrove in particular, he's been the dock master at Thales for 30 years. And yeah, I think he would quite like to retire at some point soon. It seems to me that a major driver for automation is the key person in the organization who knows how everything works is planning to retire. I have seen that in more than one project now. So yeah, their kind of knowledge of how the dock works and how things operate is totally invaluable, and really a lot of the work that we're doing is to kind of digitize the sort of expertise that they apply whenever ships are docking at present. Okay, so yeah, here's another view of the Garden Island dock. Here you can see a ship coming in, and you get a good idea of where the dock is if you are not so familiar with Sydney. Yeah, I think something to kind of point out about this, I feel like this image kind of skews your perspective on just how big this operation is, because this is an absolutely enormous ship that's coming in. Yeah, I mean, you can see down here on the dock side, these are sort of containers and, there's vehicles around. They look tiny compared to this ship, but it is a really big dock. It's the largest dry dock in the Southern Hemisphere. And it's a really key asset for Australia in terms of maintaining naval vessels and making sure naval vessels are available to do their job. But it's also a really key asset for commercial shipping as well. So for lots of significant, cruise ships, things like the Spirit of Tasmania and so on, they will come to the dock in Sydney to be maintained. Yeah, and for lots of those commercial ships, like if they can't actually use the dock in Sydney, well, the next kind of nearest option to go to for maintenance would be probably in Singapore. So it's a very kind of significant asset that's important to Australia as a whole. So, but, what is the challenge really? So the challenge is that the demand for using the dock is pretty high. And, there just is a finite capacity of how much maintenance it's feasible to do. Yeah, operational readiness in particular is a key target for the Navy. So, that means like Navy ships need to be ready to do their duty. They don't want to be sat in a queue, kind of waiting to have maintenance undertaken, because then they can't be out, defending Australia essentially. So ensuring the Navy fleet is always ready to go is really important. And yeah, as I mentioned, a lot of the large commercial ships, they don't really have another option in Australia to go to. The particular challenge that we are looking into, so between different dockings, the setup is time consuming. And so between different dockings, the dock is empty, the dock is drained, and it kind of needs to be set up again differently for the next ships coming in. And so the particular aspect of this that I'll explain more about is the kind of laying out of the keel blocks. But the whole process is very time consuming. It's very labor intensive. And yeah, there are expensive costs in terms of the materials required. And it's kind of prone to delay and disruption. And so trying to kind of reduce this downtime between dockings is really significant. If the downtime between dockings is, 4 days, often a whole week, if we can reduce that by 50%, well, typically they would have a docking at the moment kind of every 6 weeks or so. Sort of ships need to be in for about 6 weeks to kind of have all the work done on them. And then you have a kind of week period where it's then being set up. If you can reduce that time between dockings by half, across a year, you can definitely fit an extra docking in. And the amount of work and so on that goes on within each docking, that's a very significant expense. And adding that extra capacity is a very kind of important thing to be aiming for. So keel blocks. So what are keel blocks? Well, they are these things that you can see here in this image. So these big kind of concrete blocks that sit underneath the ship. So what's kind of important is every ship, has its kind of unique shape. And for every kind of incoming ship, these keel blocks need to be laid out to a particular predefined configuration. So when the ship is built, this keel block configuration that it needs to sit on when it goes into dry dock will be designed during the kind of build process, for when it's coming into maintenance. So for every ship that would come into the dock, there is a plan that defines how the keel blocks need to be laid out underneath it. So these keel blocks are pretty big. They're sort of 3 meters long, and they're about, 1.5 meters, 2 meters high. And they weigh about 25 tons. So they're very kind of big, heavy concrete blocks. And so they need to be positioned within the dock pretty accurately. So particularly for Navy vessels, lots of the Navy vessels have kind of complicated instruments and so on hanging down off the bottom of them. And the spacing kind of between each block needs to be very precise so that when the ship is laid on top of the blocks, it's supported in all the right places. If the gaps are kind of too big or something like that, you can actually get kind of bending in the bottom of the ship, which is not very good for it. And yeah, potentially if something's in the wrong position, you could damage one of the instruments or something like that as you're docking the ships, which is a potentially very expensive mistake. So here's another view of the dock, and you can kind of see these blocks starting to be laid out for one of the incoming ships. And so really the challenge is in terms of laying these blocks out. A forklift truck is used to kind of move these blocks into position within the dock. So, just to mention, you can just see it in the back of this image here. The forklift truck is not like a normal forklift. I don't know, you might see Bunnings or something like that. It's an absolutely giant forklift that can pick up these huge concrete blocks. And yeah, actually, when you're setting up within the dock, the space can be quite constrained because there's a lot of other blocks around, often they're docking more than one ship at a time. So they'll be setting up kind of 3, sometimes 4 even configurations of ships. And it's all quite kind of tight within the dock. Once they have actually positioned the blocks as well, the paneling on top, so on top of each block, there's kind of wood paneling, has to be kind of packed to a certain height to ensure that it's kind of leveled for the ship. So one thing you can't really see in this image is that the dock floor is not actually flat. So along this kind of center line is slightly raised, which is for drainage reasons. So it will then kind of drain to the sides. So it's only a very kind of slight angle, but that is enough that then it means, blocks that are not on the center line, you need to add wooden packing to raise the blocks to ensure that they kind of match the ones on the center line if you're positioning a ship with a flat bottom. So to mention also, there are different types of block within the dock. And so whenever you kind of change the configuration and you move to a new ship, you need to make sure, not only are the blocks kind of positioned correctly, but the right types are in the right position for the kind of layout of the ship. So there are about 5 different types of block. Yeah, and so again, when you kind of are moving these blocks, well, wherever possible, you actually want to kind of preserve the packing as it was from the previous setup. So whenever you undock a ship, there's always an element of some of the packing needs to be maintained because it's just had a 100-ton ship sat on top of it, so it gets a bit damaged. But what you don't want to do is kind of be stripping off loads of the packing when you could kind of preserve that kind of line of blocks and moving them elsewhere. Wherever possible, you want to try and kind of preserve that packing so that you're not using the material. And one of the reasons for that is that the wood that is used for the packing, which is a Navy standard, is actually very expensive. So often, if you have, 4 ships and, there's 300 blocks or something in the dock, the bill for wood alone for the packing can be in the kind of hundreds of thousands. So it's a very kind of expensive operation. So wherever possible, you actually want to kind of maintain the packing. So, we have this kind of complicated problem where we want to kind of move all these blocks within this kind of constrained space from whatever position they're in to whatever position we need them in as efficiently as possible. And so, the question that, kind of Thales came to us with is, can we kind of use some of the techniques from robotics planning in order to do this? And so, what's the kind of overall objectives of this project then? So we want to, develop a system to, capture some of this kind of expert knowledge that, the operators who have been running the dock for years and years do to kind of efficiently kind of move these blocks around and, eliminate some of the reliance actually on those key people. But, also in doing that, if we apply optimization techniques, we hope we can reduce both the planning time involved in actually just planning how this operation is going to happen, but also then reduce the setup time as well. And along with that, kind of reduce the cost in terms of waste material and kind of provide this baseline sort of digitization of the dock for future developments as well. So yeah, problem formulation, and here's just another view of the dock that kind of shows you, sometimes they have multiple ships in. I think for anybody that knows Sydney, you might be familiar with the Manly ferries as well. So this is maybe a kind of better reference as to how big the dock actually is. So there's kind of 2 parts to this problem. So, we can talk to the dock operators today and they kind of know the schedule of dockings that's upcoming for, say, the next 6 months or longer even. So, today we could go to the dock and we could look down in the dock and there'll be ships in there that are being maintained at the moment. In fact, I know the Manly ferry is one of those ones that's in there at the moment. And yeah, in a few weeks' time, they have a undocking that's due. And then they will be expecting a couple more ships to come in after that. So say they're expecting, 3 ships to come in after that. And then, whatever 6 weeks kind of after those ships have come in and completed maintenance, then, the docking cycle will go again. And so they might be expecting another 3 ships as kind of pictured here. And so the first kind of part of this challenge or way we can kind of think of this problem is for each of these dockings, there's different options as to how you can actually configure the ships within the dock. And so each of these ships will have under it a unique profile of how the blocks can be laid out. And so changing the actual kind of footprint of how we organize the ships, we will change that block layout. And, of course, it's the same for the kind of future dockings as well. So this kind of potentially gives us lots of different options of how we could kind of move through, this docking schedule. So yeah, once we've decided, okay, which configuration are we going to go for? Well, then, we have the block positions that sit underneath the ships. And, the question then becomes, okay, well, how do we kind of move the blocks as efficiently as possible from the first configuration to the next one that we need to? One thing I just didn't mention on this, yeah, also, often there is blocks that are not used within the docking. So actual kind of space where they're going to sit within the dock when they're not being used is an important thing to consider as well. And that's kind of what I'm representing by this hashed area here as well. Also, there's always kind of different considerations around the positioning of the ships and space that needs to be kind of kept available as well. So, for example, if, this aircraft carrier image here that I'm showing, like if it needs to have its prop shaft taken out, like you need to leave a lot of space behind the ship in order to allow the room for that. But also, say sometimes like they have to do maintenance on the dock itself, like quite often, in fact. So if a piece of the kind of concrete needs maintaining, they need to kind of keep that area free as well. So that kind of affects how you can kind of lay out the dock and how you can position the ships. And so, once we've kind of determined where the ships lie, well, then we know where the blocks need to sit. And so, how do we kind of move the blocks as efficiently as possible from one position to the other? And how do we kind of, as best as possible, maintain that packing whilst doing that as well? Okay, so, before I kind of, I guess, jump into, how we actually do this kind of, how we actually approach this problem from a technical perspective, I just thought I would talk about, what is the kind of big vision for Garden Island. And so I kind of deliberately used this old photo here of Garden Island because, to be honest, apart from the fact that you probably can't park quite as close to where the dock operations are actually happening today, it looks pretty much the same today as this photo from back in the 60s or something. So not much has changed in how it works in quite a long time. There's maybe a few more like safety handrails around and things like that. But essentially, it just works exactly the same way as it has done since it was built 80 years ago. So, with the work that we're doing, so we have this docking schedule, and what we have done is kind of develop this software to, plan the most efficient way to move the blocks from their current to target positions. And this produces a plan that the driver can follow to set up the blocks in the most efficient way. So this is one element of this work that we are hoping to do. And this is what I'm going to talk more about. But, this is part of a kind of bigger vision for Garden Island as well. So, in order for us to ultimately realize that, we're adding sensing and perception technology into the dock to kind of monitor the positions of the blocks. So whenever we need to, we can kind of draw in those positions and run our software to compute the plans of how to move the blocks. We are also looking at using, drones for aerial and underwater for kind of inspection of ships, which kind of aids with the maintenance planning, which in turn kind of impacts the docking schedule and impacts how the ships are positioned in the dock. And so it impacts, how our kind of software would then plan, where the ships are going to be positioned and how we're going to move the blocks around. We're also looking at things like actually using underwater drones during the docking process itself. I didn't really mention, but yeah, when they dock the ships, it takes about kind of 7 hours to drain the water. And then they very, very much kind of slow it down just as the ships are about to kind of touch the blocks. And there are divers in the water actually ensuring that the ships are really, really lined up on the position that they need to be. And then they very kind of gently let the last bit of water out as the ship kind of makes contact with the blocks. But, all of this as well, we're making these plans initially for the drivers of the forklifts to follow. But, ultimately the intention is that that will power an autonomous forklift, and this whole kind of operation will become autonomous. And, rather than this process taking multiple days of the driver time, the autonomous forklift can run overnight in the dark and lay out these blocks without kind of user intervention at all. So, a lot of this also kind of fits with the other work that we're doing at ARIAM. And so I kind of mentioned some of these companies that we work with before. But yeah, one project we do at ARIAM as a group, we call it our demonstrator program. So there is a ship that's owned by the Sea Heritage Foundation, which is kind of tied up in North Sydney. It's called the Cape Don. It's extremely rusted and very old. But, we have kind of partnered with them, and they kind of allow us to use it as a sort of test bed for some of the kind of technologies that we work on. And so some of our team, these images here are scans of the Cape Don. This one in the top right is a scan collected using the scanner that's made by Emerson. That's one of our partners. And this video that was playing kind of down in the bottom right is kind of made from aerial imagery by Trendspec. And so all of this kind of data collection and inspection and so on is all kind of part of this process. For every ship that Thales imagine coming into the dock, you can imagine aerial drones going out to do an inspection as the ship comes in, as well as underwater drones going and inspecting the underside. And all of that information can be kind of made available to the engineers at Thales, who are kind of planning a lot of the maintenance work and so on that needs to be done ahead of the ship arriving. This image in the middle is some of a scan initially of the kind of underside of the Cape Don. The ship has been sat there for so long, it's practically got its own coral reef grown on the bottom of it. So it needs a lot of work. But yeah, all of this kind of other work that we do in the ARIAM Hub also kind of relates to this whole kind of dock digitization that Thales envisaged for the future. So, to talk a little bit about the actual methodology, to begin with, just to say, like, this is really a learning process for kind of the different partners involved in this. I've had to learn a lot about how the dock operates and works, which has been really interesting. And we've been working with our partners at Thales to sort of educate them on the advantages of digitization and like where these methodologies and tools of robotics and so on can actually add value to their operation. And we very much tried to kind of apply this, just build something and kind of demonstrate it and get feedback and iterate on that kind of approach in the way that we work with them. So in terms of, how do we actually address this kind of block configuration question? This is a very relevant kind of problem to the field of like task and motion planning, which is a very kind of significant field in robotics in terms of, planning the kind of movements of robots, particularly robots kind of operating in the real world, and they need to kind of interact with a kind of changing environment. And so, task and motion planning particularly is relevant to these types of problems where you want to kind of plan a sequence of events, but the sequence of events is kind of impacted by the physical constraints of the real world, and each kind of task that is being carried out might kind of change the configuration of that real world space. So this is a very kind of relevant area to what we're doing, and the methodology is kind of rooted in task and motion planning. So, to give a kind of simple example to kind of get more into this problem and how we might address it. So if I just have my kind of very simple view of the dock here on the right-hand side, and I have a bunch of current positions of blocks and target positions of blocks in blue and red, respectively. And so, yeah, following, an undocking, if we've kind of decided the configuration of blocks that we then want to move to, so we know, we've decided where the ships are going to go to, and we know where the new blocks are going to go to, we want to kind of work out what's the most efficient way to actually move them. So the first thing we have to do is kind of match up the different blocks, ensuring that the type is matched across the different block positions. And, we can do this by considering, what are the feasible ways that these blocks can be moved. So we could construct a bipartite graph to represent this. And then we could kind of solve this as a minimum weighted matching type problem to find the kind of shortest distance to move each of these blocks. And actually, yeah, I mentioned, we can kind of look at multiple docking cycles with this. So if we were to kind of consider this idea across multiple docking cycles, where you could kind of imagine this graph extending to the right with more block configurations representing more dock setups. And, that kind of matching can be solved as a linear program across those kind of multiple cycles. So once we kind of matched up the blocks, what we could do is kind of consider, okay, well now how can we kind of move these in the most efficient way? And so, our first approach that we kind of applied with this problem was then to, consider this as a kind of sequential ordering problem, or really a kind of traveling salesman type problem, and kind of find the shortest path through all of these blocks. But, we have to respect the edges that we've matched up, because that's where we're actually moving the block. So we can kind of find the shortest path, but maintaining those moves within the dock as well. So once we've kind of got that sequence, well, then we can try and kind of execute that sequence and see if the sequence is achievable. So here's a sort of example of, this is a real ship layout. I think this one's actually the Spirit of Tasmania and the Manly Ferry, and we're sort of moving to another block configuration. And here what we're trying to do is we've already generated the sequence, and so we're trying to kind of follow the sequence and generate the motion here for the forklift that you can see with red and blue being kind of loaded and unloaded respectively. And yeah, what we can do is try and see if we can actually achieve that here. So here what we do to generate this path for the motion, we use this Delaunay triangulation approach. So basically I kind of scatter a load of points within this dock area. I connect them all up with a mesh, and then remove any kind of parts of that mesh that cross over blocks or collide with obstructions or so on. And then kind of find the shortest path through that mesh to create a feasible path if one exists. So the problem with this is, with the sequence previously being generated, that was not considering the actual kind of motion of the forklift. That was just considering like the Euclidean distance. And so it's only now that we're kind of considering, is the motion of the forklift feasible? And so now this methodology will actually find a feasible plan for a lot of the kind of more simple dock configurations. But, some of them are kind of much more complicated, and there's like multiple levels of blocks and so on, and things need to be done in a specific order. And then you find that the sequence is not actually feasible to achieve. And so, the first way I kind of tried to solve that was then, okay, well, once we kind of identify those moves in the sequence that are not feasible, can we kind of shuffle the sequence to try and find a new, to find one that is actually feasible? That sort of worked a little bit, again, for some of the kind of not totally simple, but still not too complicated plans. But for some of the more complicated setups, that just runs into, you just infinitely are trying to look for changes to the sequence, and you still can't kind of find a solution to the problem. So this was our kind of first attempt, and we learned a lot about how the kind of dock operates, but we needed to kind of revise this methodology. And so, this approach, doing this kind of sequential task planning and then motion planning essentially, has its problems. And so what we realized is that we needed to kind of have this more integrated task and motion planning approach. And, lots of literature tells us essentially that having a kind of more integrated approach for the task and motion planning, finds a better solution, finds kind of more optimal solutions to these types of problems. So the revised approach, if we kind of think of the block positions within the docks, if we, anytime now we could go to the dock and we can see the current positions of the blocks. And so we also then know, for the ships coming in, we know the target positions of the blocks that we want to go to. So we can kind of think of this process as a transition between those two. And so to move from our kind of current positions to target positions, there are numerous different options. If we consider a kind of graph representation where every kind of link on this graph represents a possible move, and every node then represents a new set of positions of those blocks. Of course, there are many different moves that we could make. We could choose to move many different blocks, and equally we can choose to move them either kind of directly to their target position or possibly to a temporary position as well. And so this tree, can grow, and we can progress these different kind of branches that emerge on this tree. And for every one of these links that appears, we can check, is that motion actually feasible to move from, the positions represented by this node to the positions represented by this node. If the motion is not feasible, we can kind of chop that branch and we don't need to continue searching down that branch anymore. And, of course, the goal is to ultimately find a path through this kind of growing tree that connects us from the current positions to the target positions. And so this problem, it's symmetrical as well. So we can also consider kind of looking in reverse as well. And we're looking for a path to go across. And so, of course, there will actually potentially be many options of how you could do it. And really, we're looking for the most efficient way to do that in terms of, the shortest time to position all the blocks, which really is the shortest kind of total distance traveled by the forklift overall. That's a lot. So just with this kind of revised approach as well, so I mentioned in the previous one, we use this kind of Delaunay triangulation approach for motion planning. In this kind of revised approach, it kind of changed the motion planning approach to use this kind of quad tree approach. So basically, we kind of divide the dock up into kind of different components and then consider what obstructions exist within the dock as well. So then, because often blocks are kind of clustered together, and using this approach kind of allows us to consider blocks clustered together as one obstruction. Also, often, there's deliberately kind of space left available in the dock for various things. And we don't really need to know, specific points that we could move to within space available. We just need to know that there is space available and it's kind of clear to move through there. So this is a kind of more efficient way of planning motion within the dock. This kind of integration, this ultimately leads to, well, first of all, feasible solutions for kind of more complicated scenarios, but also, more optimal scenarios as well, because that motion is actually being considered at the time that the tasks are being ordered as well. I think this methodology ultimately is kind of actually more flexible, and it's kind of more transferable, easily transferred to other docks. There are many other docks like the Garden Island dock as well. It's really robust to the kind of outlier cases, and it's kind of easier to adapt to potential changes. There's lots of changes proposed to the dock at Garden Island over the next few years. So, it can be easily adapted to them as well. So, here's a kind of example of, 4 ships in the dock here. And you can see from this animation that we're starting to move to a new configuration. So I think there are 150 blocks in this setup, which is pretty typical. So, just to note, so still the kind of first stage in this process is still to match the blocks. So that is kind of done before then using that kind of search tree methodology to actually plan the motion. So it could in future be possible to kind of combine into that search tree as well, this matching process. But yeah, as most of you I'm sure have realized, that search tree is already very vast. So, there are like 150 blocks in this setup. So there are at least kind of 150 factorial kind of branches on that tree. If you just move everything kind of directly to their target positions, yeah, much more again, if you consider you can move things to temporary positions and so on as well. So because of the sort of geometry of the dock and constraints that exist, before we kind of progress through that tree as well, we can kind of identify that some moves are just not feasible. So for example, blocks that are constrained in the middle of others, the forklift won't be able to get into them. And so this diagram here, these kind of circles, this is sort of representing different moves and the dependency of different moves that we can just sort of identify from the geometry. And so we can kind of use that to prune the tree a little bit before we even kind of start the search process. So it kind of reduces our search space initially. So if I just kind of speed this animation up slightly, what you can see is, we go from the different block configurations to, yeah, in this case, just one other ship. And then here, these are just blocks kind of sitting in storage, not being used. So, once we kind of have this search tree structure, we can potentially use different algorithms to search through that. And so here's just a kind of comparison of 2. So yeah, this is an example with 93 blocks. And so here on the left-hand side is this is using a kind of A* approach, which is finding an optimal solution. And then, yeah, here on the right is using a kind of depth-first search approach, which is a suboptimal solution, but it's a kind of quick way to, address this problem. So with this kind of depth-first search approach, essentially what we're doing is just looking for a kind of feasible route through that search tree. And so we just kind of progress forwards. And then every time we kind of hit a section where the motion is not feasible, we kind of backtrack to where we were last feasible and kind of try a different option. And so, the first thing to notice about these 2 is the difference, the number at the top. So you can see here, the depth first search found a solution, but it's got like 1,340 moves, as opposed to the optimized version, which found a plan in kind of 360 moves. And actually, if you kind of watch these 2 side by side, you can see in this top one, the forklift pretty much always travels in a straight line, and it seems very neat the way it kind of moves the blocks, whereas this one kind of jumps around a bit all over the place. It's often having to kind of go around obstructions. And so, yeah, ultimately, this one on the left gets to a much kind of higher quality solution, much better. This one on the right kind of eventually gets there, but the solution is much lower. Yeah, of course, what I'm sure many of you will realize is the computation time of the one on the right is much faster. It's about 1/20th of this one on the left. But yeah, for big ship setups of the size that we need, we can typically find a solution for anything within a kind of few hours, which, normally in terms of planning, it's not needing to be done so fast. Typically they know at least, a few days before what ships they're going to have coming in. And so the plan can kind of be generated. We still are working to speed these up and, considering kind of different algorithms. this is the optimal approach, but there will be many solutions that are kind of very close to the optimal, that in reality take just a few minutes difference in terms of the setup time, which would be more than good enough. And really the goal is to actually be able to produce very kind of highly optimal plans in kind of, the order of like a couple of minutes. So for example, though, if the driver is actually like setting up the blocks and comes to notice that one block is damaged, you might actually want to kind of replan a little bit, like almost in real time. And so having algorithms that can kind of do that really fast, I think is first of all achievable, and there is a really valuable case to actually being able to do this really quick as well. So yeah, that's pretty much kind of an overview of the work that we have kind of done in terms of the methodology and so on. But right now we're doing some pretty kind of exciting things with this project as well. So we've kind of demonstrated the ability to kind of make these plans, make feasible plans for the setup and show how they can kind of improve efficiency within simulation. What we're now doing is continuing to kind of refine those algorithms and improve the computational speed and improve the optimality. But what we're also really focused on at the moment is actually kind of making this into a prototype that we can kind of use in the dock. So yeah, my colleague Jerome, who's a software engineer at the Australian Centre for Robotics here, he's been kind of building this interface for this web app that we were just demoing this morning actually, to allow the planners to kind of interact with this code. And over the next few weeks we have some initial kind of tests in just sort of simple block configurations of using this down in the dock. And yeah, in parallel with this as well, I mentioned we are starting to kind of implement or investigate, the relevant kind of sensing requirements we need in order to kind of track the positions of the blocks within the dock, so that whenever we want to plan an upcoming docking or something, we can, at the press of a button, kind of pull in the positions of where all the blocks are currently sat down in the dock. So actually in just a couple of weeks' time, we're going to be taking some of the robotic platforms that we have here at ACFR down to the dock. Yeah, we have this robot, it's called Groundhog. It's a wheeled robot. It's loaded up with multiple camera kind of sensors and LiDAR and things like that. And we're going to be kind of scanning the dock to kind of understand measurements of the accuracy that can be achieved within the dock and so on, to help us kind of understand the sensing requirements that we need in order to do this. And so, yeah, that's pretty much everything I wanted to talk about today.